In the previous video, what did we study? We studied that about the mathematical one formula we derived, one formula we studied, correct? Now that was actually one of the parameters. That is what we call as closest approach or distance of closest approach. Now let's look at it logically. What is the meaning of it? Very simple. See, nucleus is positively charged. Alpha particle is again a positively charged particle. See, if both of them are coming towards each other, there will be electrostatic force of repulsion. Yes? Now, an alpha particle is coming with some kinetic energy, right? So that kinetic energy what we have, that is half mu square. I gave you the formula in the previous video, right? Half mu square, that is the kinetic energy of the alpha particle. And then, so how close it can come before it returns back? That's what we are trying to calculate. Because see, when an alpha particle comes very close to the nucleus, the force of the electrostatic force of repulsion becomes so much that it is forced to go back, it is forced to return back, right? This is what we are trying to calculate, and this parameter is called as the distance of closest approach, and this distance of closest approach will give you the radius of the nucleus, how big the nucleus is. Okay, let's look at the formula one more time. See, we have half mu square is 1 by 4 pi epsilon naught 2e into ze divided by r naught, correct? So r naught is 1 by 4 pi epsilon naught 2ze square by half mu square, right? Here, what are the parameters we need and what are the things we already have? See, 1 by 4 pi epsilon naught constant, we know that. E square constant. Z we know because it is gold nucleus, right? M we know mass of the alpha particle. The only thing what we need to figure out is the kinetic energy of the alpha particle. Now, for the experiment what Rutherford used, he got an alpha particle, or he used an alpha particle with an energy of 5.5 mega electron volt. We can convert that in terms of joule. 5.5 mega electron volt. When we substitute that in the formula, and of course Z value is 79 for gold, right? So if you substitute, we'll get the radius around 4.13 into 10 to the power of minus 14 meter. Minus 14 meter. Look at the size of the nucleus, 10 to the power of minus 14 meter. Size of the atom is about 10 to the power of minus 10 meter. Look at it, how small the nucleus is. So this distance of closest approach is one of the parameters to calculate the distance, or you can say the size of the nucleus. Alright. Another parameter is called as impact parameter. Now, to understand about impact parameter, let's just have a look into this image. Now, what you see here, one is you have the nucleus, correct? And then an alpha particle is straight, it's coming, but then it's not coming directly towards the nucleus. We have some perpendicular distance, right? That perpendicular distance is what we call as impact parameter. So to define it more rigorously, we can say it's the perpendicular distance between the velocity vector and the line of sight of the nucleus. The perpendicular distance what we have, that is impact parameter. Now what does this tells us? Like, what do we have from this? What can we conclude from this? If an alpha particle is coming with some impact parameter, we can figure out how far the influence of the nucleus you will have compared to the the size of the nucleus, the speed of the alpha particle, all those things. Alright, the formula what we have is B is equal to 1 by 4 pi epsilon naught ze square into cot theta by 2 divided by half mu square. This is the formula for impact parameter. Now let's see what we can what we can infer from this one. Suppose if theta value Suppose if theta value is, let's say, very large. Okay, very large. In the sense, cot theta by 2 value. See, when you look at the cot theta value, the lesser the value of cot theta, more is the value, correct? Cot 0 is infinite. Cot 90 is 0. Suppose if cot theta value is very small. Okay, in the sense, remember, I'm not talking about theta, I'm talking about the cot theta value. Right? If cot theta is very small, that means the impact parameter is going to become very small. Correct? So if cot theta by 2 is 0, that means B value is 0. Right? This is the case where the alpha particle is retracing the path. That is, impact parameter is 0. Okay? This is one thing. Next, if cot theta value is very large, then impact parameter is also very large. In the sense, the alpha particle is going very far from the nucleus. So using the impact parameter, we can figure out to what extent the influence of the nucleus is present. Like, do we have till 10 to the power of minus 10 meter? Do we have it till 10 to the power of minus 12 meter, minus 13 meter? We don't know. Because remember, in this experiment, most of the alpha particles, they just went through straight without any deviation, right? That means the nucleus has no influence till the 10 to the power of minus 10 meter. So till what distance do we have it? That we can calculate by using this impact parameter. Okay. Now these two are very important things to see how the nucleus and the atom is shaped, the shape of the atom in the nucleus. Alright. Now these two parameters. Now see, we discussed the Rutherford's atomic model. We saw what are the advantages, we saw what observations he gave, we saw a couple of parameters, what he defined. But then Rutherford model, this had some serious drawbacks, some serious setbacks were there in this model also. Alright, what are those setbacks, and how those things were rectified by Niels Bohr? First, we'll look into the drawbacks of Rutherford's model. Okay, so we'll see that in the next video.